Thank you, everyone, and thanks for coming for the talk. I know it's the last day, last talk, so I know all of you are tired, but I hope it will be fun and learning for you. So the title is Sego for Fun and Profit. There is a small subtitle there, read pain and suffering. So that subtitle is really important, and I'll get to it later. But for now, you can just assume that Sego is fun and we'll profit a lot from it. Little bit about myself. My name is Mohammed Rauf. I am a software engineer at Uber. I don't have much of an online presence, but that is my handle, and you can get in touch with me using that. So before I talk too much about the problems and good things about Sego, let me give a little bit of an introduction. What actually is Sego, and why is it very scary? So Sego is essentially a set of features or set of capabilities in Golang that allow you to interoperate C code and Go code. And what I mean by interoperability here is something I'll talk about later. Right now you can just assume that if your code main.go has something like import C, or then it means that it is using Sego in some way or another. And something there's a line right above import C, which is a comment to Go, but that is actually is called preamble, and that gives a compiler some indication on what to do when it's compiling the code. So what do I mean by interoperability? Essentially, there are two facets of Sego. One of them is that you want to invoke some C code from your Go landscape. You might want to do that for various reasons. For example, let's say you want to use OpenCV, and that library has good support and it's been written in C for a long time, and you want to invoke it from Go instead of rewriting it in Go. So how would you do that? So that Sego is a feature that would allow you to invoke all the methods and shared libraries that are available from CLand. Another facet is exporting the Go packages. So that is really interesting. So what it means is like whatever code that you write in Go, you can eventually make it available to be invoked through C. So you can export your Go funcs and add some special syntax in your code, and when it is compiled, it can be compiled as a shared object or an archive library or a DLL in Windows, for example. So my talk is mostly going to be focused on the second part, which is exporting Go packages and what are the problems that we can run into. So first, let's kind of do a little bit of a exercise on how we would go about actually doing this invocation. So there are a few steps that we need to follow. Let me just go through them slowly. So the first thing is in your main.go, you need to add import C. That is the pseudo package which enables the Sego features. And then right above import C, you add your preamble section where you give some indications to the compiler, and then you give so the main is empty in the main.go because this is not going to be an executable which is going to run by itself. It is going to be a shared object, and it will be imported, or somebody will call DL open on it. So the main is left empty. And the third thing is the export annotation. So this is kind of dim here, but I don't know if you can see the export multiply comment. So this is like a really simple method which takes two integers and returns the product. And when you add / export multiply, that tells the compiler that this needs to be exported as a C func. So now that code is written, the next thing we need to do is actually compile it. And traditionally you would do go run or go build, but here when we need to compile it as a shared object, we need to give certain special flags. For example, we have to compile it as a shared object, we will give the flag build mode and give it the name C shared. So when we do this, it will result in two files: the SO file, which is the actual binary with all the execution code, and the header file libmultiply.h, which will contain the methods that we've just exported. So same way you can do C archive, that will create an archive library. So I just want to quickly show what was in the header file. So if I tail it here, you can see there is an extern int multiply. So all of this code is generated by the Go compiler, and it is essentially exporting it as a function, and this is the C definition of that Go function, not definition, declaration. All right, so the next thing we need to do is if you want to actually compile it with our code in C and run it, so what we need to do here, I've just written this simple main.c file here, which does nothing but calls the method multiply, and above over there you can see libmultiply.h. So that is basically we are importing our method and calling it and just printing 7 into 5. So that is pretty much in the C code. For compilation, it's pretty simple, just like you would compile any C code with a particular library. Here you specify the linker location, give the library name, which is lmultiply, because we named it libmultiply. When you do this, you have a.out, and if you run a.out, it is doing the call. So this is an executable which is compiled using GCC, and we have linked the shared object compiled using Go compiler, and as a result, so this invocation is going through the Go runtime, doing all the invocation and then sending the result back to C, and here that's what you get. All right, so now that you have some introduction to CGO, I am going to switch gears a little bit, and this is going to sound like it's not a Go talk anymore, but I just promise that just keep that in mind. I will eventually come back to it. So let's do a case study. I'm calling this Pied Piper. Some of you might know why, but imagine that you have you are founder of this startup and you've invented a new revolutionary algorithm, and you have written proof of concept in Go, and you believe that this can make the world a better place or whatever. And then you have a competitor with deep pockets who is also trying to beat you. So you have a lot of pressure on releasing this new compression algorithm. So how would you do it? First of all, you also need to demonstrate the compression algorithm as well. Like by itself, it doesn't mean anything. So you decide to use video chat as a killer app to demonstrate the power of your algorithm. So the problem is we have little time and we have a lot of libraries to develop. We need a Java library for Android, iOS app, so we need a Swift library, Node.js library for some front-end systems that we have, Python library, go on and on. So we have a lot of stuff to do and we don't have enough time. So how would we do that? Yeah, so that is our problem statement here. And so let's see, coming back to CGO, CGO can be one, looks like a candidate that we can use to do something like this. Like whatever I just demonstrated, if we compile our algorithm as a library and just start invoking it from higher level languages, that way we don't have to worry about implementing the nitty-gritty details of the algorithm in each language. So we think about this. So this is like I'm setting the scene here for why would you do something like this. So we decided that this is what we are going to do. So let's build libpiedpiper.so, and that will be the library which will contain the algorithm. So just going to show a little bit of code here again. Same thing, you define your main.go, you do piedpiper.h import. So here the import in the preamble, that is a header file which contains our own declaration. So I will show that to you later as well. But otherwise you can see we have import piedpiper. That is the actual Go package with the implementation of the algorithm, and this is just the main.go which exposes those functions. and you can see compress and decompress. These are two methods which take data type, which is our custom type, take an error reference and returns the data type. Usually you would do compression using streams, but to keep things simple, let's just assume that data type will be a byte array. So let's move forward. So this was the pipepiper.h that I talked about earlier. Here we defined some custom types and some declaration for the methods that we are going to use as well. So these will be taken by the Go compiler when we run go build C shared, and it will be part of the headers and the whole binary. And this is just I want to quickly show the pipepiper.c. That's the implementation of our own C methods. So now let's develop build the library. So here I'm not doing anything fancy, just doing the same thing that I did for libmultiply before, defining a location, calling go build with C shared flag, and as a result down here in the middle we have two files again, libpipepiper.so and libpipepiper.h. Alright, so now we have the shared object. How about we try to invoke it from Python? So if you want to build this library libpipepiper.py, pipepiper.py, that will contain all the code, glue code or whatever that can actually downstream invoke the libpipepiper and return the results. So let's see how would we do that. Again, this is a Go talk, and we'll come back to it. So there are two major ways you can do something like this. Either you can build a native extension for Python, or you can do a dynamic FFI. By native extension, I mean you write some C code which does all this translation and everything and exposes and build itself as a Python module. And for dynamic FFI, I mean you just write Python code and you do import libFFI, and you at the runtime you do all the translation for invocation, and there are libraries which can help you do that, but basically that pushes it into the runtime, and that is sort of a compile time thing. And this is true for most languages. For Node, Java, you can invoke something like this using either building a native extension, or you can do it at runtime. So for Python, I'll just quickly show, like, this is going to be a bit gnarly stuff, but just bear with me, and it doesn't have to make sense as well. Here I'm building the setup.py for Python library. I build an extension. I provide sources. So here I'm using this tool called Swig that lets you generate all of that glue code that I talked about. It just helps you generate that really quickly. So here I provide the pipepiper.i, which is the input to the Swig, and we have includers, Swig options, everything. So this was our as a result of using Swig, we have these 4 files essentially. First, let's look at the pipepiper.i. That was the input to Swig. Here you can see that I've defined various methods that I want to be able to consume from Python, and this is very gnarly code. Just wanted to show you guys how the generated code looks like. All right. So this is the code that I've written myself. Here, this is not generated. Here I'm essentially calling the libpipepiper and doing all the translation and returning the results. And this builds this builds a Python module with 2 methods, compress and decompress, and which basically take a string and compress it and return it, and same with decompress. All right. So now that we've built it, let's see how it works. So this is the Python interpreter. First I import pipepiper, and then I show you various methods. You can see it has compress and decompress and other methods, and properties, attributes, but we are interested in compress and decompress. So first, let's define an input, a sort of a big input. I just define a string of size 3100, and then I say, let's call compress on it. I basically simply call the Pied Piper module and say compress it, and then I get the result compressed. The length of the compressed string is 70 characters because our string was very repetitive. Now, in order to check if it works, we try to decompress the compressed string and see what we get. So we get a decompressed string of size 3100, and then just to make sure, we'd say assert if input was the same as decompressed. So here we've done compression and decompression in Python, and all of this call has happened all the way through Go runtime. So whenever we called compress, it was doing some translation. Invocation was happening to the Go runtime. It was doing the actual call and then returning the results, and then C glue code was doing the translation again and sending it back over to Python, and then Python glue code was doing some translation and then sending it back over to us. There's a lot of steps going on, but this is how you would essentially do it though. All right. One funny tidbit, you can use Go syntax in Python. You just have to do from future import braces. If you do that, it will actually support braces instead of indentation. Just kidding. So this is a Easter egg in Python. When you do this, you get this. All right. So using the same approach, we can develop a library for Python, Java, Node.js, Ruby, Swift, PHP. Somebody might want to do that. So yeah, until now it looks fine. Like we haven't, this looks promising that we can actually develop maybe these languages. Now let's see like what happens if once we start pushing it to production. What are the problems or things? Because things break when you move to production. So let's see what happens. By the way, this was the compression algorithm. You can see I'm just using gzip here, but that's okay. Investors don't need to know that. All right. So first thing, before I put it to production, the first thing is how do we package the library? Do we check it into the code, like using Git, a large file system or something? Do we use package manager, something like brew or apt, or do we make it part of the language build? Because the distribution of this SO is very important. Each code, each library will need to know this and invoke it, right? So this has to be part, it has to be somewhere. When you're checking in, that's just an entry pattern anyway, but for package managers, it creates a decoupling between the library and the Pied Piper development cycle, but it has some other problems. So like we have like these three ways of doing it, but none of them have like a really strong answer. When you build with each language, the build runtimes, the build times of the language library go up. So there are various problems with each of these approaches. But you know what? Like right now, we're just going to go ahead with it, and we'll just since we are a startup here, we just check in the binary. All right. So what's the worst that could happen? And so I apologize for using an outdated meme, but all right. So the first bug. What is the first bug? Application failed to start. So we are running into the same problem that I talked about. The SO file has to be there for the libraries to work, and for some reason or another, like if, for example, if we're using brew or apt-get to distribute the binary, it's possible that the hosts that our app runs on, the binary didn't get deployed. And then at runtime, you start getting these error image not found when you're trying to load the library. So like this is scary, but we can work with it. We can do something, make it part of the build runtimes or try other approaches, make sure like fail it cleanly at least and raise an alert, doing something like this. This is still tackleable. But once we fix that, we go into a second bug. What's that? All right. Segmentation faults. So this is quite scary. So we have essentially, this is like super scary, right? You don't know where it could be coming from. Is it coming from Python glue code? Is it coming from C? Is it coming from somewhere in Go? Because when you're using Go runtime and Go runtime doesn't know about C code doesn't know about Go memory, like there's a huge swath of problems that could have, it can be coming from anywhere. So, and then debugging is really difficult. But for now, let's assume that we were able to find a bug, we did some debugging, and we fixed it. Moving on, we run into another problem. What's the worst that can get? But out of memory. So this is the symptom of memory leak. Somewhere in our whole stack, we have a memory leak, and we don't know where. And like our app, this is very hard to debug as well because the app keeps running, and at some point the memory is full, and it throws an out of memory exception. So how do we deal with this? Again, there are some tools like Valgrind you can use, or something like you can do some benchmarking, profiling to figure out. Still, it is problematic, but we can still try to use it somehow. Moving on, we have one final thing that kind of puts the last straw into the problem. It's like final nail in the coffin, if you may. So here, this is a web server, dummy web server, which is running, and it is listening on port. And after a while, the app hangs. Like, why would it hang? So most of the time when something like an application hangs, it's a result of a deadlock. So how did we get into a deadlock here? So let's kind of unpack that a little bit. So when we run our application and we import the PyPiper module, for example, here, that eventually goes and loads the libpypiper.so, which contains the whole Go runtime. And at your application, when you import, the whole Go runtime starts in the background, and it is taking care of all the things, running all the threads for memory management, Go routines or whatever. And then you call the method, and then all the way from Go runtime gets a result. The problem is that in Python, a lot of the web servers and like a lot of libraries like Tornado, they rely on process forking for handling new web requests. So whenever you fork a multi-threaded process, you run into problems, because forking was developed way back then when usually it was a single-threaded application. So when you fork a multi-threaded process, the thread where it forked from, only that thread remains in the child process. So as a result, when a Go runtime process is forked, the new child process will not have all of the Go runtime necessarily, or maybe if the Go fork happened from outside the Go runtime threads, the new process will not even have the Go runtime. So like there are a bunch of issues that you run into this. One of the symptom is deadlocks. It's like when one Go runtime instance is holding on to some memory, and then another child tries to hold on to the same memory, and as a result you get into weird situations, and this is like one major problem. And yeah, so this basically puts the whole thing into a disarray. Like we can't really fix it. So if we have to fix it, we have to use multiple heuristics. Either you have to wrap it in separate process, like whenever your Python process forks, your child process should not fork at all, and you do IPC, some sort of communication to do the results, or you do post fork hooks. With post fork hooks, what would happen is, like, whenever the Python process will try to fork, it will first go to the post fork method, and in that hook you define that you want to unload the Go runtime and load it again. So you can do bit of heuristics to tackle this problem, but this is at this point getting too much. Like, where do we put the stop? So so initially it seemed promising to use Sego, but once we actually dig into it and use it, this doesn't work anymore. All right. And the problem is, I've just scratched the surface here. This is just the start. Like, if we go into it, there are a lot of other problems. I'll just go through them really quickly. First one being debugging. How do you debug something like that? Once you go into runtime crashing, or when you have memory leak, or even let's say if you have a normal bug that you want to debug, your normal debugger won't work. If you want to use GDB won't work with Go runtime easily. So it's very, very hard to do debugging. And second problem is versioning. What happens when the library that you have, which is the libpiper.so here, and the higher level library, they go out of sync. There is a glue code which works with older version, and then the older version gets replaced and this new versions comes in, and then you have problem of how do we reconcile these two libraries. So that's a problem that we need to tackle as well. Third thing being the invocation cost. When you invoke something that goes all the way through the Go runtime and then gives you the result, it's not cheap. You have to take into account all the things that happen. Like at each glue code layer, you do the invocation, copy the stack and everything, and then call the function, and then coming back and then returning the results. So all the, not the stack, the copying of the parameters and then translating them to the target language. This is like a lot of stuff going on there, and this is not cheap. So you have to be mindful if it is in your production code, and it can induce some latency there. Another thing is the context. In a lot of modern applications, you use something like tracing or matrix or some other type of contextual information, and when you call the Sego library, all of that information is lost. Essentially, you have to marshal all of your parameters, all of your context into the call, and then take care of that in your Go code. So this is again a lot of work, and sometimes it's not possible as well. For example, let's say you are passing in a tracer, and then that tracer needs to be instantiated in the Go runtime as well. So this is again a little bit of a problem. We have signal handling issues. So Go runtime takes over the signal handling. So as a result, Python signal handlers, they get overtaken. So you have to be mindful. You have to like take the ownership back there, and you have to be mindful. Otherwise, the developer experience will be bad. When you press Control C won't work anymore because the Go runtime eats the signal. So you have to be mindful of that. Another thing is async methods. What I demonstrated was pretty simple, like a method. You call the method and get the result back. If you want to pass in a callback and want the callback to be invoked once the work is done, that's a little bit of a problem. It can be done, but you have to wrap it in various ways and make sure your callback has a wrapper somewhere in the glue code which does which takes care of the memory, and then you have to make sure the Go memory and the C memory they remain separate. You do not pass in a method which resides in the Go memory. So there's like lots of stuff you need to do to take care of that as well. So what is the takeaway from this talk? Should be pretty simple. That is the takeaway. So Sego is a Pied Piper and not the library, and we were basically led to a very dark place. And while it looks promising, it has a lot of hidden costs. And while in the beginning you thought, oh well, we can develop so many libraries easily, at the end you find out that a lot of work was put into tackling a lot of those problems that arisen later, and basically this is...
It's okay. Thank you again.